I'm Anil Kumar. In this particular video, we'll discuss about continuity of a function, and I hope that will give you good practice for your test on this topic. I'll also provide you with links with some test questions. So we'll discuss these four topics: continuous or discontinuous functions, reasoning about continuity at a point, we'll investigate continuity at a given point, and then we'll look into piecewise functions and continuity criteria. Now, to talk about continuous and discontinuous, let me sketch few functions here. So I'll sketch four of them. Continuous means that the graph of the function has no breaks, right? So is continuous means without any break. That's what it is. So let's say if I have a function which is kind of like this, let's say going upwards. Now this is without any breaks, right? So it's a continuous function. It may start from a given point, right, and go anywhere, but within the domain of this function, we say that it is absolutely continuous. In fact, I should say that within the interval shown, there are no breaks, and therefore the function is continuous. Functions could be having a break like this. For example, a function could be like this and something like this. Now here you see that at a point, let's call this point as A, there is a discontinuity, right? This kind of a discontinuity is called jump discontinuity. We could also have a break which could be like this. Now, this function is continuous at each and every point except for, let's say, this point A, where we have a hole not filled in, right? So at this point we have a hole, and this is called point discontinuity. We might have functions, as you see, like 1 over x kind, where you may find asymptotes, the vertical asymptotes. So here there is a discontinuity right there at x equals to 0. Now this kind of a function has a vertical asymptote, right? So we have vertical asymptote. And we call this as infinite discontinuity. So these are different types of discontinuities. As you can see, all these functions which I have drawn here, they are having some kind of a break. So jump discontinuity, a point discontinuity, which we treat as a whole, and infinite discontinuity as the function value approaches infinitely large value for any value in between. In this case, it happens to be at 0. Now the criteria for continuous function is, let me write down the criteria here, and then we'll discuss it further. Is that we should have limit of the function. Let's say we are talking about continuity at point where x is approaching a, then the limit of the function at a from the left side should be equal to limit of the function at a from the right side, correct? And this should also be equal to the value of the function at a. So f of a is the value of the function at a, right? So what we say here is that the limit of the function exists at a right? This is f of x. Limit of the function exists at a, and it is same as its value at a, right? So any point a, if you check here, then we see that the limit and the value of the function is same. In these cases, limit may exist from left side or right side. It does not exist at a. Then we have jump discontinuity. The limit exists from left and right side, but it is not equal to the value of function, and therefore the function is discontinuous. That is point discontinuity. In this case, the limit does not exist as we approach 0. The function approaches undefined value, and it has infinite discontinuity, right? So I hope this point is well taken care of. And now let's move on and explore this definition with the help of an example. So we'll reason out about continuity at a point with the help of this piecewise function. So the question is the following function continuous everywhere? Function given to us is a piecewise function, f of x equals to x minus 2 for x less than 3, x squared minus 8 for x greater than 3, and at x equals to 3, the value of the function is 1. So let me sketch this function here, and then we'll discuss continuity. So what we are given here is that at a point 3, the value has a value 1. When we are talking about less than 3, then it's a linear function x minus 2. For x greater than 3, it is a parabola, x squared minus 8. So let's say this is 1, this is 2, this is 3, let's say 4, 5. So this point is 3 for us. And let me draw the first function. If we are on the left side of 3, that is to say, if I make a table of values here, for different values of x, I will write the value of f of x. So if the value of, let's take few values. So if I take 3 examples, right? So at 3 it is 3 minus 2, which is 1. Add 2, since it is less than 3. Add 2, it will be 2 minus 2 will be 0. Add 1, 1 minus 2 is minus 1, right? So if I take, let's say, 0, we get minus 2, and so on, right? So if I plot these values, what do I get? At 3, I get a value of 1. At 2, it is 0, right? At 1, it is minus 1. So it's kind of a line going like this. Since it is less than 3, we'll make a whole open circle in this position at 3, correct? Since it is less than 3. Now let's look into the second piece, which is a parabola. So if x is equal to 3, we have to take the values of x from 3, let's say 3, 4, and 5, for example. So if I write 3 here, 9 minus 8 is 1. If I write 4 here, 16 minus 8 is 8. And if I write 5 here, 25 minus 8, we get another value. So let me write down, show it on this graph. That's a very high value, so I'm not taking it, right? So the value of the function for these values will be sketched as a parabola. So let me use another ink for this portion. I could sketch this piece as, we are saying greater than 3, not including 3. So at 3 it is 1. So again the same point. So let me make a bigger hole now. Okay, so this is 1. And then at 4 it is 8. So let's say 1, 2, 3, 4, 5, 6, 7, 8. Let's say this point, right? So it's a parabola going like this, right? Now that is the second piece. Now we are also given here the third piece, which says that at x equals to 3, the value is 1. So at 3, we just fill this up with 1. Do you see that? So that is the third piece. So now you can see that all the 3 pieces are joined together, right? So we have a continuous function here. right? So what we notice here is that the function is continuous. And we can reason it out like this. If I find limit of the function f of x as x approaches 3 from the left side means this side, right? Less than 3. In that case, we are on this part of the piece, x minus 2. The function f of x approaches a value which is 1. So the limit from the left side is 1. Now if I find the limit of this function as x approaches 3 from the right side, we are on that part of the piece. So if I substitute 3 here, 9 minus 8 is 1. So we get the value of this limit as also 1. As you can clearly see, these two values are same. And therefore, we can say that the limit as x approaches 3 for the given function is equal to 1. So the limit exists. So first thing is that the limit exists. The second part is that this limit is also equal to value of the function. So what is the value of the function at 1? At f of 1, the value is, at f of 3, at 3, the value is 1. Now since the value of the function at 3 is also equals to limit of the function as x approaches 3, we say that the function is continuous, right? So that condition, this condition, which, let me write here, value of the function at x equals to 3 is same as its limit x approaches 3, right? Therefore, the function is continuous at x equals to 3, right? So that's very important. Individually, all pieces are continuous, right? All these are continuous in the entire domain, right? So we know if it is less than 3, we have a continuous function. If it is greater than 3, it is continuous. And in between, the limit is same as the value of the function, right? Since the limit as x approaches 3 for the function is equals to the value of the function is continuous in its entire domain, correct? So that is what we understand by continuity. So this function given to us is continuous in its entire domain, right? Let's take up the next example now, and this time we'll investigate continuity for the given function g of x. Now let us take another example and we'll investigate g of x, this time for continuity. It's a piecewise function, 3 different pieces. When x is less than 1, we're talking about absolute function. When x is between 1 and 2, 1 included, it's a parabola. And when x is greater than 2, it's a constant function x equals to 3, right? So let us first sketch this function. Once you sketch a function, then by seeing the graph, we can easily conclude continuity, right? So let's sketch it. We are saying when x is less than 1, it is like an absolute function, absolute x. You can make table of values that will give you a very accurate graph. So I'll just make a rough sketch. So at 1, it is 1. Since 1 is not included, I'm putting a hole here, correct? At 0, it will be 0. And absolute function is always positive. So the graph will be kind of like this, correct? So that is my first piece, right? Now let me sketch the second piece, which is like a parabola. So if I substitute 1, I again get this value. Now this is filled in, right? So I'll fill this up. Do you see that? So I'll take a filled in circle. So at 1, 1 square is 1. It is between 1 and 2. Now, at, if I take 0, it is 0. So at 2, it is 4. So at 2, it will be, this is 1, this is 2, 3, and 4. So it's a parabola. So I'm trying to give it a shape of a parabola, right? So it is kind of like this. However, 2 is not included, and therefore I'm making open circle here. And the value for 2 square is 4. Correct? So that becomes part of second piece. The third piece given to us is x is equal to 3. So let's say this is 1, this is 2, and that is 3. And it also includes the value 2. So at 2, it is 3. So at 2, it is not 4, but 3. So it starts from somewhere here, below this point, correct? And it is a constant function, which is, 3, right? So this is g of x equals to 3, right? Beyond 2. Clearly, you can see that this function is continuous at x equals to 1, right? But discontinuous at 2. We have a jump discontinuity. Do you see that? So we can conclude that the function is continuous at x equals to 1, and we have jump discontinuity at x equals to 2. And reason is that the limit of the function as x approaches 1 from the left side, the function is g of x, is equal to limit of the function as x approaches 1 from the right side, right? And both are equal to 1. However, limit of the function as x approaches 2 from the left side, if you approach from the left side, right, then you reach a value of 4. This is 4. And the limit of the function g of x as x approaches 2 from the right side, if you approach from the right side, you're along this horizontal line, you approach a value of 3, and they are not equal. Now, since these two limits are not equal, limit does not exist. So the limit as x approaches 2 does not exist for the given function. Well, if the limit does not exist, then the function is discontinuous, correct? So therefore, it is discontinuous. Now, since there are different limits, since the limits are different, the type of continuity is jump discontinuity, right? In the first case, we see that the limit is also equal to the value of the function at 1, right? At 1, right? Yeah, at 1. Since the value of the function is same as the limit, the function is continuous. Do you see that? Limit exists and it is same as the value of the function, and therefore the function is continuous. So I hope with this example the concept is clear. So for a continuous function, limit should exist and it should be same as value of the function. If it is discontinuous, limit may exist or may not exist. I hope with this example the concept is clear, how to analyze a piecewise function and figure out whether it is continuous at the joining pieces or not, right? So let me take another example. Now that's the last example for this exercise. The question here is, find k if f of x is continuous. F of x is given to us as equal to x plus 3 where x is not equal to 3, and x plus square root of k when x is equals to 3. Now individually, we know first piece is a straight line, right? This is a straight line. Whose domain is x belongs to real numbers. But since We are not talking about a point at 3. In this case, the domain x is not equal to 3. So we can sketch this part of a straight line. Let me sketch it here. So x plus 3 means y-intercept is 3 and slope is 1. Kind of like this, right? At 3, let us say 1, 2, 3. So at 3, we have a hole. It's not filled in, right? And that's the line. So that's what I'm trying to say. Correct? So this is first piece. The second piece here is a constant. The second piece here, this one, is a constant line. It's a horizontal line. Right? But this is only valid for one value, right? So normally it would have been a horizontal line. But since it is only valid for x equals to 3, it is just a point. Is it okay? Where the x value is 3 and y value is 2 plus square root k. So at 3, depending on the value of k, it could be any point. Do you see that? It could be any point. The question is, find k if f of x is continuous. Now to make it continuous, this value of 3 should be equal to that value to make it continuous. Do you get an idea, right? So from here, as you can clearly see, at x equals to 3, for f of x to be continuous, value of this function, which is 2 plus square root of k, should be equal to value of this function at x equals to 3, right? 3 plus 3. So at x equals to 3, it will be 3. It should be 3 plus 3. Now that equation helps us to find the value of k. So square root of k is 6, taking 2 to this side, which is 4. So k will be square of 4. That is 16, correct? And therefore, we have our answer that k equals to 16 for f of x to be continuous. But that gives you the basic understanding of making a piecewise function continuous, right? So I hope this criteria is very clear. Feel free to share your suggestions and views, and if there are questions, post them. I'll provide you with links where some selected questions have been taken from previous test papers. Practice them so that you are absolutely ready for your own test. All the best, and thank you for watching.